All right. Ready for another day of Advent of Code. We are just getting started here, ready to tackle day 16. I have not had a chance to get caught up with day 15 yet, but we will knock out day 16 here. All right. Let's get cooking. Two minutes and 6 seconds left. All right, I'm excited for today. We'll see what we get. Should be interesting. Been pretty successful so far. I've started working on day 15. I'm going to do that off stream. So you can see I got through 1 star so far. Maybe we'll do it at the end of this one. If it goes well, we'll see. Kind of unsure. Well, today we'll go. All right. Let's see here. Whew. About to get started. Yeah, sorry I missed everybody last night. Saturday nights, Sunday mornings are kind of my day to rest. So didn't really do a live stream, or really wasn't on at all actually. So just trying to get caught up today. But I thank everybody for coming and hanging out. Should hopefully be interesting. We'll see how we do. Just got a few seconds left here. All right, let's dive in. Day 16, Reindeer Maze. It's time again for the Reindeer Olympics. This year, the big event is Reindeer Maze, where the reindeer compete for the lowest score. You're the historian. Historians arrive to search for the chief right as the event is about to start. It wouldn't hurt to watch a little right. The reindeer start on the start tile marked S, facing east, and need to reach the end tile marked E. They can move forward 1 tile at a time, increasing their score by 1 point, but never into a wall. They can also rotate clockwise or counterclockwise 90 degrees at a time, increasing their score by 1,000 points. To figure out the best place to sit, you start by grabbing a map, your puzzle input from a nearby kiosk, for example. There are many paths through this maze, but taking any of the best paths would incur a score of only 70-36. This can be achieved by taking a total of 36 steps towards and turning 90 degrees a total of 7 times. Here's a second example. In this maze, the best path costs 1104. Following one such path would look like this. Note that the path shown above includes one 90-degree turn at the very first move, rotating the reindeer from facing east to facing north. Analyze your map carefully. What is the lowest score a reindeer could possibly get? Okay. So I think this is just path finding algorithm. Let's see here. Yeah. So we can just create a heap, create a queue, and then the less scores when we analyze next. Obviously, every time we take a turn, that's going to cost us, but you can see here this is cheaper than going up here and going this way. So we would know that, and we would just follow the cheapest all the way down and around, etc., until we get to the end. I don't think it would make sense to go any other way. And then in that, we can just mark our visited queues so that we can mark the score along with what's visited. We can revisit a spot if we get there from a cheaper perspective, and then go from there. I think that'll get us there. So just use some Dijkstra's maybe. So we're gonna use a heap for that. I actually did this on day 9 or 11, I think already. But on that day, no, not 9, maybe 10. I think I deleted the code. So yay for me. Maybe not 10, maybe it's 11. That's okay. We have another example of a heap in this code base, so I'm just going to grab that and we'll start there. Yeah. So the part that kind of stinks with Go, at least right now, is that these aren't done with generics at the moment, and so you pretty much have to create a whole new like priority queue, and that's the part that really stinks is doing all of this. But I'm going to copy it so I don't have to do it, and then we should be good to go from there. Right, I'll move this down here and we'll call this priority queue, and this will be just a path, and our path doesn't have anything crazy in it, except it does have a, we'll keep the row and column, don't care about the heat loss. We'll keep the row direction, column direction, and we'll put in a cost in here, and I don't care about the index as much. And then this will be pq dot cost, we'll call it, and then I guess we could use the index for that. Swap the indexes, and then this is going to be path. And we'll do that. So now we need to load the grid. So the grid input looks like this. Let's get this input here, and we'll put that in our test, and we'll catalog that here. And so the next part is just implementing this. So first we want to load the grid. So I think we don't really have any, like, yep. So that's fine. So that's our grid, and then we're going to find our start. And then And then to say what direction we start in. The reindeer starts in the star tile marked S facing east. Okay. And then does this say, note that the path shown above includes 190-degree turn as the first move. So, okay, so we do start east and we can't go east, but we can go north. So does it say we can turn clockwise or counterclockwise? Let's see here. They can also rotate clockwise or counterclockwise 90 degrees at a time, each increasing their score by 1,000. Does that mean we can move clockwise twice? I mean, what if we want to, or counterclockwise twice? I mean, that's essentially 180 degrees, the opposite of what it's facing. Hmm. Okay. Looks like it. So we can technically turn around, I guess. But if we're retracing our old steps, we kind of want to stop the pathing, right? So we want to knit our heap. Yeah, let's do that instead. And then yeah, something like this. And we know it's just path. I didn't call it city block. Probably needs a better name, but we'll go with that for right now. So this is where we are, and our initial direction is east. So our we're going to push onto the heap our path. Yeah. And then for our path, we want our start sub 0 for row. Our column is going to be start sub 1. And then our row direction is going to be right, because that would be our east. And then our call direction sub 1. And then what else we got in here? Our cost is currently 0. think that's it. Yeah, we don't care about the index. Okay. So that's our start. And so we want to pop the next thing off of here. And what we want to do is we want to go in all directions, right? So if we it doesn't really actually matter the direction we're going in except for the cost multiplier, right? So yeah, so we want to go in all directions. So we'll say for and we'll start by just saying p dot I think they were fair enough to surround us with with the endpoints. So we really want to do any checking here, but we can say if first we just want to check is it a valid square. So if p dot row plus dir sub 0, and then we'll say g dot column or p dot column plus dir sub 1. If that is equal to that, not that, then there's nothing for us to do. Otherwise, we want to talk about cost. So if dir equal to p dot row direction dir sub 0 actually let me change the order of this. I prefer this to be on this side, and p dot column direction so really dir 1 then our cost is going to be 0, or sorry, our cost is 1, right? So if we're going the same direction, the cost is 1. So really, we can say that. So how do we determine if it's 90 degrees versus 180 degrees? So if it's this, that's 180 degrees, right? So if our row direction is equal to our column, and our column is equal to our row, no. So we're going east. So that should be the opposite, right? So if it's 0, 0, if it's 1, it'll be -1. And so if this is true, then that's actually going to be 2,000, right, for our cost, because it's 1,000 per 90-degree turn. So where is that? Yeah, 1,000. Might be a better way to do this, but I'm just going to go with this for now. Just make this a function. I think it'll be easier. So cost is going to be equal to, just call it C. Probably remove this function call here in a second, but P dot row, P dot column, and then, sorry, this should be row direction, P dot column direction, and then the direction we're headed. So that should give us our cost. So if it's this, we return 2,000. And this will just be R and C. R, C. And then if R not equal to dir sub 0, or R not equal to dir, it's supposed to be C, but we'll go with that. Then we return 1,000, otherwise we return 1. I think that's right. And then so cost is that. So we return 2,000 if it's the opposite direction, 1,000 if we are going in an alternate direction for either row or column, otherwise we return 1. Meaning they're not equal the same. And then so this should just be heap dots push, push this point. And it should just be basically this with a few modifiers. So cost is going to be C, but it's going to be P dot cost plus the new cost, right? Because we're going to add on whatever that cost is. The direction is going to be whatever dir sub 0 is. The other direction is going to be dir sub 1. And the row and column are going to be this and this. I think that should be right. So we're going to pop those onto the stack. The one thing here left is, do we care about revisiting squares? I think we do. I think it would self-rectify anyway. But if we already know we visited a square at a cheaper cost, we don't want to revisit it later. So I think the way we handle that, I'm trying to think here, we can just keep a map of visited, and it could just be but we'll keep a map of path, and that way we can check and we can say, okay, if visited, we'll move this, but we'll call it func key, and we take in rc int, and we return a string. So we just do this real quick. Yes, we'll do p dot row, p dot column, and we'll go with yeah, we're gonna have to, we'll do it as we process each one on the cost. So like not when we add them to the stack, but as we process them in the stack. And so we'll say if visited, we'll say if p dot cost, we'll call this b instead. If that's less than our p dot cost, then we are going to continue. So if the previously visited cost is less than the current path cost, then we're just going to continue not process it. Otherwise, visited equal to p, right? Oof. I'm sure how I feel about that, but that's okay. We'll go with it. Right, so we are here. So now, in theory, if we were to loop through this, if our and our p dot column, if we are on end, do we not return p dot cost? Is that not true? Okay. 11048. 11048. Why am I off by 37 points? Or I mean, why am I off by 11 points? If my visited cost is less than my p cost, then I continue because I don't need to reprocess it. We're not off by a major amount. it's almost as if I'm missing something. Okay. Let's see here. We're close. We're close to the test. We just got to figure out where I am missing. Where am I wrong at? That should all be right. Plus dir 0, p dot column plus dir 0. It's p dot cost plus c. So whatever our current cost is, what is our starting cost? Does it say what our starting cost is? The reindeer starts in the start tile marked S facing east and needs to reach the end tile marked E. They can move forward one tile at a time, increasing the score by 1 point, but never into a wall. They can also rotate clockwise. To figure out the best place to sit, you start by grabbing a map, your puzzle input from a nearby kiosk, for example. There are many paths for the maze, but taking this, blah, blah, incur a score. But taking a total of 36 steps forward and turning 90 degrees a total of 7 times. Here's a second. Okay. So am I too high or too low? That's the question. My actual is 11037 and the expected is 11048. Okay. So how would I have came in lower? Make sure I got my score right here. They can move forward one tile at a time, increasing their score by 1 point. Okay. 36 plus 7. Yeah, so that's right. I don't know what I was trying to do with calculator. But okay, so we only that seems right. Let me make sure I copied this correctly. Maybe I goofed the copy. We could only hope, right? Don't think so though. If only it could be that easy. Um hmm. So I think what I might want to do, got a couple of options here. Um, I could like track the appended stack and kind of walk through that. That's one option. So that's the up, down, left, and right. If where we're going is wrong, we're going to check p.row direction, column direction versus dir. dir right 1, column direction. So this would indicate that we are flowing right. And we would check that versus each time. In our row, it's going to be the row in the direction we're heading. Our new row direction, new column direction is that. And our cost is always going to be the cost plus C. And so I'll know the cost for going here. Okay. I think I need to just add a path. And then when I get to E, I'll print the path. I realize that's a bit more data, but I think this is just the best way to debug it because the question is, do I... Yeah, so I think we only add it here. Is the append of p dot path, which I realize I'm calling it path, but that's okay. Whatever the path was, and then whatever the source is, right? So that would be our p dot row, p dot column, I think is what we want to do here. And then when we get here, let me see if it's not going to be pretty, but maybe we can look at it real quick and figure out our problem. If not, I will have to reconsider. Okay. So 15.1, 14.1, 8.1, 7.1, 6.1, 5.1, 0, 1, 2, 3, 4, 5. So 5.1, 5.2, 5.3, 6.3, 7.3, all the way down to 15.3, and then 15.4. 1 second. Oh, 15.5, 14.5, all the way up to 13.6. Hold on a second. Wait, no, that's wrong. Hold on. Fifteen four, 15.5, 14.5, 13.5. So it decided to go right here. I think the problem is that the E that I have, the first one I'm finding, well, no, because this is a cheaper path though. So if the problem was that I was finding a more expensive path, then okay, but that's not the problem here. So I mean, is it possible the test input's wrong? We're not off by 1,000, so I don't think that's the issue. But well, I know what the issue is that it starting at 13.5. This is 1, 2, 0, 1, 2, 3, 4, 5. It goes up to 13.6. Oh no, I'm sorry. It goes this way. And then 13.9. Then 10.7. Then 9.7. $14.5. One, two, three, 4, 5. 14.5. 13.5. 13.6. 7, 8, 9. Then 10.7. How do I get to 10.7? I think there might be some funny business here with some of the pointers. I'm going to dereference that. I'm going to dereference that. So okay. If RC, I think all that should be fine. But my path is wrong. Why is it jumping paths here? 13.9 to 10.7. Path is the P dot. Oh, let me copy this just to make sure, because call it a clone. There we go. Let me just make sure that's not getting clobbered under me. It looks like it may have been. Not that that's my problem, but that may have given me some false information. So 14, 15.4, 15.5, 14.5, 13.5, 12.5, 11.5, 15.5, 14.5. 15.5, 14.5, 13.5, 12.5, 11.5, 11.6, 11.7, 10.7, 9.7, 9.8, 9.9, 9.10, 9.11, 9.7, 9.8, 9.10, 9.11. Hold on a second. Where did I go from 9.7, 9.10, 9.11 to 8.11? 0, 1, 2, 3, 4, 5, 6, 7, 8, 10, 11. Oh, I guess that is 11. 0, 1, 2, 3, 4, 5, 6, 7. Because I just can't count. 8, 9, 10, 11. Okay, so that's 9, 11, 8, 11, 7, 11, 7, 12, 13, 14, 15. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And 6, 5, 4, 3, 2, and 1. Okay. So we don't have the 1 in here. So why is my cost wrong? Starts in the start tile marked S facing east and needs to reach the end tile marked E. Move forward one tile at a time, increasing their score by 1, but never into a wall. They can also rotate clockwise or counterclockwise 90 degrees at a time, increasing their score by 1,000. Man, I'm missing something pretty obvious here, for sure. But I also feel like it's pretty subtle. 15.1. The 14.1. Is this 16 here? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Oh, wait a second. That's interesting. Okay, I think it is actually because I'm rotating then taking the step, I think I actually have to add +1 to these. Does that solve my test? Yeah. Yeah. Okay. So let's get our puzzle input. Let's give it a shot. Mm, um, 141 seems pretty low. Did I run the wrong day? Hold on. Yeah, that's funny. Okay. I was running last year's test. It says part 2, but part 2 is just really running part 1. So we'll go ahead and submit that. Okay, awesome. Let's go to part 2. Let me change one thing before I even look at that. I'm just going to get rid of this print statement. I'm going to leave this on here just in case I need it, or it might be interesting for visualization later. Now that you know what the best path looks like, you can figure out the best spot to sit. Every non-wall tile, S period or E, is equipped with places to sit along the edge of the tile. While determining which of these tiles would be the best spot to sit depends on a whole bunch of factors: how comfortable the seats are, how far away, etc. The most important factor is whether the tile is on one of the best paths through the maze. If you sit somewhere else, oh, what got me into coding? I've been a software engineer for a while. Um, Merry Christmas, I see. But I started out in high school, believe it or not. I just kind of got into like web design. Anything really with computers seemed to interest me. And over time, it just, the interest grew. And then that kind of developed into just an interest to dive in more. And then it turned into a career. So, it's just about diving in and seeing if you like to solve problems. I mean, most of your real world problems are not going to be like additive code puzzles. They're actually, in my opinion, much easier and simpler to solve. Um, but yeah, feel free to ask more questions. But yes, it started with good old HTML. We'll start there. And then it moved on to PHP and then Python and now Golang. Although there's some C# and .NET sprinkled in there and some other things. How comfortable the seats are, etc. It's where the tile is. If you sit somewhere else, you'd miss all the actions, so you'll need to determine which tiles are part of any best path through the maze, including the S and E tiles. In the first example, there are 45 tiles marked O that are part of at least one of the various paths through the maze. In the second example, there are 64 tiles that are part of at least one of the best paths. Analyze your map further. How many tiles are part of at least one of the best paths through the maze? Okay, I don't get the trick here. Everything marked S period or E is equipped with places to sit along the edge of the tile. While determining which of these tiles would be the best spot to sit depends on a whole bunch of factors, how comfortable, etc. The most important factor is whether the tile is on one of the best paths through the maze. If you sit somewhere else, you'd miss all the action. I mean, okay. I mean, did I already solve this? Is this already solved? I think this is already solved. Here, here, let me just create a part 2 for no reason, because I don't want to condense my code right now. And then I'll refactor it here in a second. But did I already solve this by just doing, do I just got to do length of p dot path? Is that is that my second test? Part 2 here. Do I what's part 2? What's the, is it 64? Is that what we're looking for? Actual 48? Looking for 64? What's the first one? 48? In the first example, there are 45 tiles marked O that are part of at least one of the various paths through the maze. It says various paths, though. At least one of the best paths. But what's considered one of the best paths? What does that mean? So are we guaranteed to have multiple paths then? Like if we go if we go up this way, or if we go over and then up, are these both equivalent paths? Is that what we're being told here? And so I don't think it's solved, but I think it's close to being solved. So I think I have this length here, and I think the problem is that right now I'm only checking the top path, but I'm missing the, we'll just check it right now. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 additional. 48 plus 15 gets us to 64. Gets us to 63. Plus 1 for the start. I think that's right. Might be right. Okay, so at least I understand what the problem is. So now what we have to do is I can create a best path, and I can leave that at we can do this then. So instead of returning here, we're going to continue here, and we're going to say that best path is equal to path right. So now we've got best path, and best path is equal to we're going to call it basically this here. And we'll call it actually it's just P. It's just P. We'll dereference it though. Yeah, it's just, if I can find the right key. It's just P. So now we can continue. Now we found a path. The cheapest path. Anytime we process P, if just say not equals 0, and best path or end P dot cost is greater than our best path dot cost. If that's true, then we continue. Why? Because if we know we're on a path that's greater than what our best path is, we're going to keep processing, but we don't want to continue to process after that. And then maybe we call this best paths and we just give it a slice. And then instead we say if length of best paths greater than 0. And we'll just, if that's true, we'll just always take the 0 index one. And I think that'll be fine. And then what we'll do is best paths equal to the append of best paths P. So we'll always append onto it. And then our score at the end is going to be, it really should just be best, yeah. We'll call it seats. Why not? So it should be, yeah. We'll just create a map, a string, because we've been doing that anyway. And we'll just call it bool. And we'll say, no, we don't want to create that yet. Oh, yeah, we do. Actually, I take it back. We'll say for path in range of best paths. And then we'll say seats, and we'll say key, path dot row, path dot column equal true. And then we could just do length of seats, right? Come on, test, run faster. I should increase the time on this. It did already run, probably. Oh, am I not running it? That'd explain a lot. Oh, best paths. Yeah, my bad. So we actually got a range over the path dot path. That's terrible stutter, but I'm here. I don't care. And then this should be post sub 0 and post sub 1. Okay. If our lengths are greater than 0 and best path, just make sure my test here is running part 2. It is. It is. It is. Um. Oh. Okay. So I think what's probably hindering me is my visited code. Um. No, if my visited cost is less than my P cost. So it should continue. Yeah, only if the visited cost, if visited cost is less than the P cost, we continue. If they're equal, it should continue. If the P row column is E, then we append it to best paths and we continue. If the P cost, oh, okay, hold on, is greater than best path, that cost, that's probably what it is. Hmm. Let's just see what we're getting here. I think we're not getting to 2 paths, but not 100% sure. So we are appending here, so I'd expect us to append. Yeah, length of best path is 1. Okay, so if we're here and it needs to go 2 ways, we're going to continue here and pop off the heap. What happens when I do this? Do I get multiple paths now? No. Why shouldn't I? Okay. Yeah. So we do need the visited in here, otherwise we're gonna go backwards, right? Not everything is gonna get to end eventually. And so we do want to catalog. I wonder if instead of so E, that final point in the stack, oh, I think I understand. So I need to, because we always want to visit E. Yeah. So now we got two paths. Is it that we don't want to dedupe them? No, we definitely want to dedupe them. But why are we missing 3? I mean, we could be missing the end node, right? Because in the path itself, we don't include the end. And that would put us at 62. And I'm pretty sure we don't include the end node. Let me print them out real quick just to make sure. But I think that is that issue. So if we let's do best paths sub, let's just do 0. So we start at 15.1 and we go to 2 and 15. Yeah, so we don't have the end listed. So that's +1. And I think we have the start listed, which is 15.1. Let me go look at this in the test file. Yeah, so it's 15.1. I mean, I could print the grid if we want and see what the difference is. I think it's the best way to kind of debug it at this point because I am missing something. I have the 2 paths now, but I am missing, I know I'm missing the ends. That's a problem. But we can add those here because we'll do yeah, so if we rerun the test, it should give us 62, but we're still off by 2. So we're missing 2 somewhere. Yeah, because we want the... We don't need best path anymore. We can do seats. We want to get the true number here. But that should give us a like a 1 in 15 or something. Yeah. And then we should also have a 15.1. Okay. Yeah, let me convert this to yeah, actually we'll do it right here. We want to change that, but we will change these and we'll say G sub 0 sub 1 equals to O. And then we'll do a print line G dot pretty. Okay, well, that's a bit different. So I didn't take the down route, but it took this up route. Oh wait, maybe we need to do one other thing here. No, best paths. This puts us back down to one path, huh? So it's not taking this route here for some reason. Oh, I see the difference. I see it. So when we get to here, our cost. So what's happening is this. When we get to this corner here, at the position in this corner, my cost currently is what it is. When we come from this direction here and we get there, it's the same cost, I think, or it's more expensive. But then this makes a turn, and so this path is cheaper technically once this makes a turn, but we don't see that. So I think what we have to do with our visited is we could add direction to that. And I think that will do. It'll expand how much we're like kind of going out there, but let's see if we can, if this will work. P dot row direction and P dot column direction. So we catalog the direction in which we're visiting from as well to make sure that if we're coming from a different direction, we'll in fact catalog those. There we go. Okay. So yeah, that's what was happening is that I wasn't getting that last little bit of calculation. I was missing the fact that there was a cheaper route without the turn because I wasn't processing that second path because it was going to be a straight as opposed to a turn, and the way I was processing those scores were kind of different. So let's see 531. 531. Awesome. All right, cool. Well, we just finished what day is it? Day 16 of Advent Code. That's pretty awesome. Man, got hung up here on a little bit of a bug, but we are good to go. Anybody have any questions or comments? Anybody stuck and need some help? I think I might try to finish up day 15 here. If anybody wants to hang out for that, but day 16 is done. Let me get rid of some of the logging here. Nice, nice. What's kind of cool is we could probably actually visualize this pretty easily. Um, what's our grid size look like here for the input? It's kind of big. It's kind of big. Yeah. You want to see if we can visualize it real quick? Here. So, because the way I built things here, what we can actually do is, let's actually change this to be a slice of int. Because if it's a slice of int, then we can actually just, and we can add, actually this could be a, yeah, it could be that. And then we can take that and we could say grid dot fill display dot new, and we'll call this m g, and then we can say what's up, hoodwink da don. Do you have a question? Waiting. Let's try it. See what happens. See if we can get this thing to display for us. Well, that happened kind of fast. Kind of cool, kind of fast. Let's let me just do something real quick. Let me turn this into 50 milliseconds for this particular go around. Slow it down just a tiny bit. Oh, nice, nice, nice. So what I did was I actually reordered the slices, thinking that maybe we could, that was a good idea. It was not. So here, let me close out of this, and then we'll come back to here, and we will switch this instead of using this unique set. That's kind of useless for what we're doing here. And for our cells, we can just Yeah. It'll be fine. It'll color the first one through. It'll make sense. The second one through won't make so much sense, but it'll be okay. This isn't quite visualizing Dijkstra's, but at the same time, it is kind of showing us what the optimal path is through. Oh, I did transform them to O, so that kind of also throws it off here. But this does give us an idea of what it looks like. Now, what I can do is go back and change it so that it shows the actual walking of the paths, and then anything that is an edge to the walk, it could mark that as red, which would give a slightly different pathing for it. And then so we can kind of see where it stops, and as it picks the more optimal paths, and then once it's done crawling, we can come back and mark everything as green. I think that would be pretty interesting. But we'd have to do some more like Go routines and possibly some channels there. But it's kind of interesting, like the different pathing it's taking here. So this is walking the path once it's fully complete, not as Dijkstra is visualizing it. But maybe we could like do something a little bit different here if we're interested. And you know, if we really wanted to visualize it more, we could dive into the visited here. What we would want to do is, I think each time we would go to a cell, we would color that cell. So what I can do is I can do a weight group here. And then I'll go funkify this. Yeah, like that. And then we'll just do a we only need to add one. And then if we come back here, we can done that here. And so that will tell us when we're done, and then we can and so now well, what do we want to do here? I don't want to do this anymore. So what I'm trying to do is articulate like how we want to display this data. And so the problem is that we have this display window. I know from using find this has to be in the main thread because of some garbage collection issue. So in order to do the coloring outside of that, we were doing this, which is fine for the final pass. The best paths could be set inside, and so could the seats. I just need to do these before scoring. These don't actually have to come before the display, I don't think. So we switch that. What this means then is each time we come into the heap, we can I really should have created a separate function for this, but it's okay. I'll do that later. We can then I'm going to move this up here. And then I'm going to color each time in here as I visit. So I'm going to do d.color cell, and I'm going to give it a p.row, p.column, and I'm going to give it a display dot, let's call it red. Yeah, something like that. So now if I run this, what you should see, I'm hoping, is that as this runs, it runs incredibly fast, and you've got the entire grid lit up in red in no time. All right, that's too fast. So is this not delay? No, it does not. Okay. So maybe we could... I think I'd rather create a channel so that we can have all the processing done, and then we can come back and look and see what's actually happening here with the Dijkstra's algorithm. So you can see it crawling down below. This is just a way to visualize it. It's kind of a neat little different perspective. Kind of see how it crawls. Trying to get to that end state and trying the different paths. I'm just visualizing Dijkstra's at this point. Essentially. I'd say it's a bit slow here at that pacing. Let's try like 10 milliseconds just to kind of speed this up a little bit. Let's filter this to go. And we'll kill that. Yeah. There we go. It's a little better. Now we're actually like getting through visualizing this algorithm. We're just building some visualizations here. So if you're joining and you have some questions, feel free to ask. Part 2 has already been complete, so I'm just kind of doing some additional follow-up stuff here. Just kind of visualizing that the Dijkstra's algorithm a little bit and kind of see what I built and how it looks. As far as implementation goes. Kind of gives you an idea of the pathing that it goes through the crawling here. What's kind of interesting is the pathing for my particular example just goes far right and far up. So it takes like a right and up path. And so a lot of this initial cost analysis here, it ends up crawling the entire grid anyway by the time we're done. But neat little visualization. Yeah. All right. Anybody else have any questions? Oh, I already finished him. I'm just visualizing now kind of the what it looks like. I'm just kind of curious what it came out to be. But essentially, yes. Really in the end game, I did pretty much crawl everything. But you find the initial first best path, and then you need multiple best paths, right? In my case, there were several. I guess there was only two in the actual test. Yeah, yeah. This is just a visualization. I kind of built this like grid library, if you will, and I've been messing around with being able to like visualize these things so that like as we crawl them, we can just do some neat things with like not just building the algorithm, but what does it look like? Uh, and so I did get hung up at one point where visiting a point in the grid and not my visited did not have the direction in which it was entered in, and so the second path wasn't being found because the first path was actually making a 90-degree turn after visiting a location, which gave it an additional 1,000 to that total cost. But when the other path, which was coming at a straight, missed it, that caught me up for a little bit. But just doing some post game right now. Oh, I don't even know. I didn't check. Here we can go look. I don't particularly get on the leaderboards, I don't think ever. Or like 121, 24-11. So looks like I might have beat your rank just by a little bit here. So the reason I was kind of a little bit ahead of the game, yeah. So that was the issue is like I was just marking visited without the direction, and so um, because I didn't catalog direction of my visited, it tripped me up on the second path being or one of the other paths. Yeah, surprisingly, Tim, you've been pretty spot on with some of these, so I am surprised myself. But what I think saved me was while we're letting that kind of run and visualize. In part one, I went ahead early on because I was kind of planning to do some visualization here. I added where's my well, I'll just go to my path. I added a path early on for testing, and I used that to help with the debugging. So I already had a lot of the framework set up for part two with my priority queue, the heap here. And so I was able to utilize that um, in part two by just copying and pasting essentially what I had and then tweaking it a little bit as far as, whether or not we were going to catalog more paths or not. Um, and so I had a lot of that data already there. Yeah. So this is going to crawl the entire thing. So I'm just going to kill that. And I'm going to undo my funkification here with lots of command Z's. part 2, I started at the end and went backwards looking for states that were either a return 1,000 less or a move in 1 less. Well, interesting. So all I did for part 2, let me copy this function real quick. And I'm going to change it to I can come back to it. All I did for part 2 was pretty much my part 1 implementation. Just make sure it still runs. I'm gonna have to kill it. Yeah. Yeah. So, I mean, it takes 5 seconds to run. It's not super crazy efficient. But yeah, so part 1 and part 2 are pretty similar for me. The difference with part 2 is that I have this slice of best paths. Path is probably not the best term here. This really should be tile. Path is the tiles in the set, so I should refactor that. But best paths is fine. And so what I did was just use a heap. So I put the starting position on the heap, and then for that I pop each item off the heap. And if we've exceeded the length of best path, or if our length of best path is greater than 0 and the cost of the tile that we're on is greater than our best path, then I exit some really exit conditions. If I end up at E, then I append that to my best path list. In theory, we should have found the best path on the first pass. And then really we're just looking for any best path after that. And then, of course, we add to a visited list, and we don't visit it more than once if the cost of the visited is less than our current point. And then the thing that tripped me up for a few, I don't know, 10, 15 minutes is I didn't have the direction in my map. And then it's pretty much just going through every direction and incrementing the cost. So, all right, I'll give you an opinion on that. So I do a lot of backend services in Golang, and one thing that is probably the most frustrating piece with Go is when you're working with other services that are less statically typed, like JavaScript as an example. You can create custom marshaling for that, where something that might be a string or might be an int or might be a bool, very frustrating to work with, in my opinion, because we are dealing with statically typed languages. And so you have to understand how to handle that. But you can create custom unmarshalers on fields. And that actually helps a lot once you understand that. So that when you receive something, instead of it forcing it to be a string or an int, if they send you a different type, you could do the type conversion yourself. So that's one thing that helps a lot. On the flip side, if you're writing a service in Go, because it's statically typed, you end up creating very good services for consumption, because the end result that you produce is pretty much guaranteed, which is why I like to write a lot of my services in Go. But I also consume a lot of services as well. So, one of the things I've written in my company is I wrote what we call a real-time command interface, but engine, but it was a tool that allows accessing to different parts of the network via an API to execute certain commands, store that data, parse that data, and present it to users who are executing those commands in a real-time interface. And so there's an API backing for that. So the front-end interface can just hook into it. What's IRC? or just IRC. I just might not be familiar with the acronym. Oh, if I recall correctly. My bad. Yeah, so like you can do something on structs like you know, if you look at the oh yeah, I'm sorry, the internet speech, my bad. Um yeah, that's quite a bit of time ago. Yeah, no, you can do some really cool stuff with like custom marshaling. So I like one of the things that I've had to deal with is poorly written software and poorly like designed timestamp fields because a timestamp can be in multiple formats and for some reason people can't get that right. And so marshaling that into Go is somewhat of a challenge, and that's a pretty common like issue. So if we had like a person, which is a struct, and then that person, you know, had some sort of like hire date, maybe. Well, if you use like a JSON.time or a time.time field, depending on your format, this may not marshal incorrectly with like a JSON on marshaller or with database if they're sending you like poorly formatted dates. But you could also do like a type custom time of a time.time, and then on this you can create a func I think it's called like unmarshal, if I'm not mistaken. I have to look here. I can look here in a second. But then you would use this as your custom unmarshaller, and I think it just takes in byte data, if I'm not mistaken, or byte. And so, and then this would actually not be a string. This would be a time.time. And then you would do your custom unmarshaling here to convert a given input or set of inputs or case statement of inputs into a set of data. And so then this becomes, so now, you know, if they give me 5 different formats for hire date as an example, I can handle all of those conditions inside of here, inside the, I wouldn't probably call custom time, but just as an example. And then that way we can interop with whatever interface on the unmarshal and the marshal side of things. It definitely takes way more work than in something like Python or something like that. But the product at the end of the day is worth the extra effort. I think I've got that correct. It's close enough. Anyway, so it's been pretty fun. Anybody else have any questions, concerns? Yeah, so day 15. Last night I was not well, let's just say last night was my night of rest. So I actually have a start of day 15 that I started today. Um yeah, so I got the first part knocked out. Um Here, we can look at what I have. Run the test. Oh yeah, no, this is why. So I am a sucker for recursion. Um, in other words, I'm a glutton for pain. Um, so here's where I'm at. I got part one done pretty easily. I just took a recursive approach and more or less um, yeah, what I essentially did was on each part moved. Yeah, exactly. So I actually think my part two will be fine. Part one was worked perfectly well. So essentially I created this move function. And then in this move function, I look forward and, if we're this, we remove false. And if we're this, if we're an O, we check to see if we can move. And then we just recursively check for the move. What didn't work? Are you talking about your like taking the recursive approach or what your approach was? Oh, you tried to paste your code. That's probably what happened. Yeah. So I just went this route, and this was pretty easy for part one implementation. The problem is with part two, that's not so easy to do. And so my part two looks a little bit uglier because I was determined. Um, yeah, that's exactly what I did, right? So I said, hey, if we can move, move. So in part two, what I'm doing is essentially saying like, hey, if we're going left or right and we're one of these, we know that we can just it's movable, just move to the next one, right? Um, but if we're one of these and we're the other direction, we really should add the opposing side. So if this is the left side, we need to also add the right. And if we're going the other way, um, then we need to add the left. So we always add itself and the left side. Now, I can see how they'd be problematic because, yeah, what I'm not doing right now is I'm not um, checking to see if this point that I'm adding is already in my list. And that's my current issue. So I think if I solve that, this probably isn't an issue anymore. I spent 40 minutes. I think I started at like 11 o'clock Eastern tonight before my live stream started just to see if I can knock this one out. Um, yeah. But if you're just joining, day 16 is already done. So we're just kind of waiting or messing around with day 15 because I was not here for that. So I think in this case, I actually want to check these slices to see if they're already in here and then to not do them again, essentially. So we really want to create a unique set of this. So yeah. I'll just do the poor man's way. It's all right. These are all just points, so they're pretty small. So we could just do Yeah, so I'm going a recursive approach as well. Um, Recursive approach. I just the thing is the unique points, right? For me, uh, which this isn't super efficient, but I think this will get me through. Gotcha. Interesting. So let's see here if I do that and then I do outs equals to append outs r, and then I just do a mv see if that just does what I need. Nope. Yeah. So the idea that I have here, and maybe it's too much, but we start with a set of points, which the initial point is just yeah, that is true. That does help. I think so. We don't actually return the actual points here. We just check in the direction that we need to go, which is right. And then we unique them each iteration. And then we move them all at once. And then we move forward our piece. Yeah, so what I did was, and I think this is okay, I just think I have a bug somewhere, is left and right is easy. Establish that. But if we're on the left bracket for one of the points that we're looking at, we check and we grab not only that point, but the point to the right of it. And that is based on the current point that we're on. So where the robot is, we check the direction of that point. So if it's above, that's what we're checking. And if, of course, if it's this directly, that's going to stop us. But otherwise, we append to a movable stack things that might be movable, whether or not they can be moved. And then we take that set and we loop through those points and we look at all of the things above it. So it's a slightly different approach of like get each layer and check each layer. And if any one of them in that layer is not movable for some reason, then we return false. But if everything can be moved, and so I think the reason why this is not very efficient is because on the input, um, we would potentially have all of the layers from a particular direction, like kind of stacking up, so to speak. But I guess that would really be up and down. It wouldn't really be left and right, but still. Yep. Yep. Yeah, that's what we're doing here. Because we're only adding the things we need to check next if the box is there. And then we're essentially trying to return that whole entire stack and then say, okay, move that whole stack at once. Um, Obviously it's not working, so I have something wrong here. Mm. I could take another approach and not do recursively at all. Um, or we could just loop through the points and essentially add to a queue or a stack and then process those and then take them off the stack. I mean, that's an option too. But I don't know why. So movable should just be our next points in a given direction. They should never be the current point. So, I mean, eventually we should get to the end of the stack and it should bubble back, but it's not. So I'm doing something probably very subtly wrong. I don't really think we have that many levels to prevent the recursion approach that I'm doing now. As we go through each like layer and we say, okay, here are all the things we need to check. And if none of them are invalid, we move to the next layer. minus 1. Oh, I is greater than 0, I minus minus. It's going from the back of the stack down, which is what I want. Yeah, we need to add day 15. Let's do it. Oh yeah, I can read Python for sure. I mean, it might take me a second, but I spent probably like 3 or 4 years writing Python for a past company, doing like conversions and things like that. So I mean, if you got some code to share, feel free. I think I'm pretty much on the right track here. I just gotta get my focus right. I'm missing something pretty obvious. So we're never getting through the first iteration. So movable is our initial cell location, RR and RC. Yeah, you're gonna have to figure out another way to share the pseudocode because it's not coming through the chat. I think I just realized. No, that's left. So we want right. And which means that this would be the opposite, which is the right side. So we want the left. In addition to the point we're on. No, you'll probably need to like make like a gist or some sort of page that you can share. That's what I did the other day. There was someone else that was sharing some code, and they ended up going to a GitLab page. I don't remember who it was. I think his name was Caleb on day like 8 or 9. Or no, it was 9, I think it was. So that should be good. Okay, hold on. I think this is it right here. We need a if length of points equals 0, return true. I think that's what we need. I think that's why I'm like recursively in this stack forever. or not. Okay. Let's see here. Nothing new in my output. So I know if we don't have any points, we want to return true because then we don't have anything left that is movable. Okay with that. And yeah, so what should happen is we get that initial point. This is the plan or the strategy. We get that initial point, which is where the robot currently is. And we have the next row, next column assigned to P0, direction 0, P1, direction 1. And we get that value. And if the value is hash, we return false and an empty set. That's not super important. And if we're going left or right for the direction, if the grid dir left, if the incoming direction is left or right, it's one of those two conditions, then we append on any square bracket. Like, we know that's movable, right? If we're at a robot and the next thing is one of these squares, we know it's movable until it gets to a hash. If then that value, if our direction is not left or right, then we know we're going up or down. Doesn't really matter. Right. And so we check to see this continue should be fine. We check to see if it's a left bracket. If it is, we add the right. And if it's a right bracket, we add the left. So I think this logic feels okay. Maybe I don't need that. Definitely need something. So, I mean, maybe I am exceeding the movable. But we shouldn't be if any of the values are this. I mean, it's not a huge... maybe that's not a crazy amount. Yeah, I think I just need to move away from this recursive call. And instead, I mean, I can just, let me try a new part 2. Because I think I could use the same technique. I could just not be so recursive with it, and or not like actually use like a recursive function, but rather what I can do is I could just create a stack, and we can say like, if not, we'll just continue because there's nothing to do there. And we can say, why is there not a pop function? Just want a pop function. The things that made me go, Um, yeah, there we go. And then I can essentially do what's inside here. Yeah, no worries, Tim. I was kind of done for the night anyway, so I might just end the stream here, and I'll come back and finish up day 15 probably in my own time. But it's good talking to you. I'll see you tomorrow night, hopefully. You have a good night. All right, well, thanks for joining, everybody. It's a successful night, and appreciate everybody hanging out. Unless anybody else has anything for me, I'm going to call it for tonight. But y'all have a good night. Bye.